All right, let's jump straight in. We're looking at a really fascinating new paper today. Emu3.5. Native multimodal models are world learners.
Yeah, this one's making waves. It feels like a pretty big step in unified generative models. If you need the quick takeaway, the 60-second version, here are the main points.
Okay, hit us with it.
So Emu3.5, it's a huge model, 34.1 billion parameters. And the core idea is it's a multimodal world model. It's designed to natively predict the next state across both vision and language.
Natively predict, so not just processing them separately. And how do they build this?
End-to-end training, unified next token prediction. And the data set scale is just massive. Over 10 trillion interleaved vision language tokens.
10 trillion, wow.
Mostly from sequential video frames and transcripts off the internet. That's the world learner part, learning from sequences.
Got it. But big models often mean slow inference, right?
Yeah.
Especially for images.
Exactly. Which is why their other big contribution, Discrete Diffusion Adaptation, or DiDA, is so important. It's a lightweight tweak, really.
Lightweight, what does it do?
It basically converts the slow, sequential, token-by-token image generation into a bidirectional parallel process. Think diffusion, but for discrete tokens.
Okay, and the benefit? Speed.
They're reporting roughly a 20x speed up for image inference per image, and crucially, without hurting performance.
20x faster with no performance hit.
Yeah, it's significant.
Yeah.
And it let them achieve state-of-the-art results, beating competitors like Gemini 2.5 flash image. They call it nanobanana in the paper, which is kind of funny, on really complex stuff.
Like what?
World exploration, embodied manipulation, things that need that long-term consistency.
Okay, let's unpack that foundation a bit more. This idea of a unified generative framework, predicting the next state across modalities. It sounds very ambitious.
It absolutely is. And the scale, 34.1 billion parameters, with 31.2 billion just in the transformer layers. It's a beast. It's a decoder-only setup, 64 layers deep.
64 layers. Whoa.
Yeah.
And they're supporting a huge context link too, right? 32,000 tokens.
Yep, 32,768 tokens, which, to make that stable at 64 layers deep, you need some serious engineering.
Right. That's where things like grouped query attention come in. And RMS norm, QK norm, these aren't just buzzwords here, they're probably necessities.
Oh, absolutely critical. Especially QK norm, when you're dealing with that many layers and that much context, keeping the attention mechanism stable, making sure it doesn't just sort of lose focus or collapse, is paramount. QK norm helps manage that attention distribution.
So it lets the model actually use that massive 32K context effectively, especially for long video sequences?
Exactly, because if you want to model a world, you need that temporal depth, but then you hit the next problem. How do you efficiently represent the visual part within that context window?
Tokenization.
Yeah.
Always a bottleneck.
Right. So their total vocabulary is huge, over 282,000 tokens. It's split about 151K for text reusing the Quen tokenizer, and then 131K dedicated vision tokens.
131,000 vision tokens. That's a lot. They're using something called IBQ for that, right? Can you remind us what IBQ is?
Sure. IBQ, improved blind quantization. It's their method for basically taking an image, the pixels, and compressing it down into a sequence of discrete tokens the transformer can understand.
Okay, what's the breakthrough with it in Emu3.5? Just a bigger codebook.
The bigger codebook helps, but the real win is efficiency. They managed to get better reconstruction quality, clearer images from the tokens, while using only 1/4 of the tokens the previous Emu3 model needed for the same image.
Wait, 1/4 of the tokens for the same or better quality?
Yeah.
That's huge. That means you can fit way more visual information, like longer video clips, into that same 32K context window.
Precisely. Massive compression gain. And they also mention optional decoders if you need even higher fidelity.
Optional decodes.
Yeah, diffusion-based ones. They can apparently generate images at double the resolution compared to the standard decoder, and they sped that up too.
Oh.
Using LoRa-based distillation, they cut the denoising steps needed from 50 down to just 4. So like a 10x speed up for that high-res diffusion decoding path offers flexibility.
Okay, interesting. So great architecture, clever tokenization. Let's pivot to the training. This world learner idea hinges on the data, right?
Absolutely. The scale is, again, staggering. Around 13 trillion multimodal tokens for pre-training.
13 trillion, and you said mostly video.
Overwhelmingly. Sequential video frames and their transcripts from internet videos. This isn't just about image-text pairs. It's about sequences, time, context.
Why is that so critical? Why not just use, trillions of static image caption pairs? What does the video sequence give you?
It gives you the world part. Static pairs teach alignment. This image shows a cat. This is the word cat. Video inherently encodes spatiotemporal continuity.
Like cause and effect.
Exactly. Causality, object permanence, how things change over time. If the model sees someone pick up an apple, then take a bite, then the apple has a bite mark. That's way richer than just seeing pictures of apples. It's fundamental for reasoning, planning, understanding actions.
Okay, that makes sense. And they did this training in stages.
Yeah, two main stages. Stage 1 was the bulk, 10 trillion tokens, focused on getting that basic cross-modal alignment and temporal understanding down.
In stage 2.
Stage 2 added another 3 trillion tokens, but shifted focus. Higher resolutions, up to 2024 by 1024, and incorporating much richer annotations.
Richer annotations like?
Things like semantic segmentation maps, detailed summaries, fine-grained visual captioning, really trying to enhance the model's understanding of scene details and its ability to follow complex instructions.
This two-stage approach, massive alignment first, then refinement seems common now. Is there a risk, though, that stage 2 messes with the foundation built in stage 1, like shifting the data distribution too much?
It's always a potential concern in stage training, but the idea is stage 1 builds the robust core understanding, and stage 2 adds layers of detail and control on top. And critically, the next steps, the fine-tuning and RL, are meant to properly integrate everything.
Right, the post-training. Let's talk supervised fine-tuning. SFT. I think it's 150 billion samples. That's a lot of fine-tuning data.
It is. And the goal was broad. Establish a single, unified interface for all kinds of multimodal generation tasks.
All kinds. Like what's specifically?
The paper lists a bunch in Table 3. General stuff like text-to-image, basic vision language tasks, but also specialized things. Any-to-image editing, X2I, generating visual narratives, step-by-step visual guidance, that world exploration stuff, and the embodied manipulation tasks. One model to handle all of it.
Ambitious. And after SFT comes reinforcement learning. For final polishing.
Exactly. Large-scale joint RL. And the key here was designing a really comprehensive reward system to guide it. It wasn't just about make the image look good.
What made the reward system comprehensive?
They focused on 3 aspects. First, generality. Basic stuff like image aesthetics, prompt alignment. Second, task specificity, using targeted metrics where needed. Like for text rendering, they'd use OCR-based squares to reward accuracy. For narratives, maybe metrics for temporal consistency.
Okay, general rewards, specific rewards. What's the third?
Unification. This is maybe the trickiest part. They had to take all these different reward signals, some about pixels, some about text accuracy, some about story flow, and normalize them.
Normalize them how?
Into a single combined reward space, scaled from 1 to 10. This is super important so that when the RL optimizes, improving one aspect like text clarity doesn't accidentally break something else like image coherence. It balances the trade-offs.
Right, turning it into one big optimization problem. Okay, so they build this incredibly sophisticated model, trained on sequences, fine-tuned across tasks, polished with RL, but we come back to speed. Sequential decoding. That's still the elephant in the room for image generation, right?
It's the fundamental bottleneck of autoregressive models for vision. Like you said, generating a high-res image, say 124 by 124, might need, 4,000 tokens with their setup. Doing that one by one is just slow.
How slow are their baseline tests?
They mention up to 120 seconds, 2 minutes. For 120/34 image.
2 minutes. Yeah, that kills any kind of real-time interaction, any agent trying to see and act quickly.
Totally unusable for that. And that's precisely where DiDA comes in. Discrete Diffusion Adaptation.
Okay, break down DiDA for us. How does it escape that sequential trap?
It's pretty clever. It adapts the math of diffusion models, which are normally used for continuous pixel values, to work with their discrete visual tokens. Instead of generating token 1, then token 2, then 3.
It does what?
It starts with an initial guess for all the visual tokens at once, maybe just random noise or a corrupted version. Then it refines that entire sequence in parallel over a few denoising steps, from sequence completion to parallel refinement.
Parallel refinement. That sounds fundamentally different. But trading sequential dependency for parallel speed, does it compromise quality? Did they lose anything in that 20x speedup? Maybe subtle details or complex structures.
That's the million-dollar question, right? And according to their results, no, they specifically checked this. DiDA maintained comparable performance on both standard text-to-image and the trickier any-to-image editing tasks.
Comparable performance at 20x the speed.
Yeah. That 4096 token image generation time dropped from 120 seconds to just 10 seconds. It basically brings the speed in line with fast continuous diffusion models, but using their native token-based architecture. That's the win.
10 seconds instead of 2 minutes. Okay, that makes it practical for interactive use.
Exactly. But then you need a system to manage this, right? Sometimes you need fast sequential text generation. Sometimes you need this fast parallel image generation.
How do you switch between them efficiently?
They used the flag scale framework and built a novel scheduler based on a finite state machine, an FSM.
An FSM scheduler.
Think of it like an air traffic controller. It knows whether the model needs to be in text generation mode, sequential, or image generation mode, parallel DiDA. It manages those transitions smoothly so the whole process feels seamless for interleaved tasks, like a conversation with images.
Very cool. Okay, so architecture training, massive speed up. Let's get to the payoff, the performance. How did Emu3.5 actually do on these challenging tasks, especially against competitors like Nano Banana?
They did extensive benchmarking, often using ChatGPT as an automated judge for preference evaluations, which is becoming a common approach. And the results really highlight the benefit of that video-based training.
Where did it shine most?
Particularly in tasks needing long horizon consistency. Take world exploration. This is where you give it prompts like explore a modern living room, and it generates a sequence of views as if you're moving around, turning, looking at different things.
That requires remembering the layout, object positions.
Exactly. Spatial and temporal consistency. And here, Emu3.5 got a strong preference win rate against Nano Banana, 65.5%. It was better at simulating that consistent virtual navigation.
Okay, that's impressive.
Embodied manipulation. This is huge for potential robotics applications. The task is to break down a long instruction like fold the clothes into key visual steps, maybe simulating what a robot arm like the Songling Aloha would do.
So understanding physics, object interaction sequences.
Right. And here, it had its highest win rate, 67.1% preference over Nano Banana. It shows a real grasp of planning and sequential action representation. Maintaining the state of the clothes being folded across frames is non-trivial.
Definitely. What about more narrative tasks?
It did well there, too. Visual guidance generating step-by-step visual instructions for something like how to make Italian rissoles. It won 51.5% of the time there.
Aligning language steps with visual changes?
And visual narrative, generating a story with consistent characters and scenes over multiple image-text pairs. They used a fun example like Isaac Newton faces off against Sonic the Hedgehog. Here, it won 49.2% of the time. Still competitive, showing good long-term coherence.
So clearly strong on sequences. How about core image generation and editing quality? The fundamentals.
Also very strong state-of-the-art performance in T2I and X2I. One standout capability is text rendering within images.
Putting readable text onto generated signs or labels. That's notoriously hard.
Extremely hard. But Emu3.5 outperformed previous SOTA models on English text, rendering benchmarks like LexBench and CBTG2K, and it got the top score on long text bench for English rendering. That precision is a good sign of its underlying visual understanding.
Yeah, if it gets text right, it's probably handling fine details well. What about editing existing images? Any to image X2I.
Achieved state-of-the-art there too, particularly in complex open-world editing based on instructions. High scores on benchmarks like ImgEdit and GetItBench.
You give an example.
Yeah, things like viewpoint changes, convert this scene to a bird's eye view, or really specific object manipulation, find the object labeled 4 and change it into a movie poster. It shows it can parse the instruction, locate the target, and perform the edit accurately. That world knowledge from videos pays off.
Okay, let's try and wrap this up. EMU 3.5. It feels like a major statement. They scaled up native multimodal training massively, using primarily video data.
Right, proving that a unified next token prediction approach can handle complex, long-horizon vision and language tasks effectively. That 10+ trillion token video dataset seems key.
And then they tackled the critical inference bottleneck with JIT.
Yeah, that discrete diffusion adaptation, giving a 20x speed up for image generation without sacrificing the quality gained from all that training. That's arguably just as important as the scale itself. It makes the power usable.
And it's fantastic they're committing to open sourcing the model and the whole development process, data pipeline, tokenizer, training details, DiDA itself. That's a huge boost for the research community.
Absolutely. It lets others build on this, verify it, push it further. It really accelerates the field.
Okay, so here's the final thought to leave you with. We've seen EMU 3.5 demonstrate high-fidelity world exploration, complex manipulation planning, and narrative consistency, all combined with that dramatic 20x speed-up in visual generation thanks to DiDA. It feels like a threshold has been crossed. So the question is, now that we have models capable of this level of consistent, long-horizon visual reasoning, and they can generate the visual outputs fast enough for interaction,
What kinds of truly complex multi-step agent applications suddenly become feasible? What opens up when visual planning is both coherent and fast?